Good morning, folks. I hope you're doing well. Let's go ahead and get started with our matter and units of matter measure lecture. Let's see if we can make some sense out of this material for you. I'm going to go ahead and share my screen. And I'm actually going to share that one. And let's see what we can do. So we're going to talk about matter and units of measure. In doing so, we're going to be talking about classifying matter. We're going to be talking about making measurements, things that are important to making measurements, dimensional analysis. Those are the things we're going to cover today. Now, there is another lecture for significant figures. Make sure that you go through that. It gives you some idea of what the rules are. All of the same slides are presented here, but it is another place where we talk about what do those things mean, so that in case you need to go to review them, that's been pulled out for you. Okay, so that's what we're going to be talking about today. So normally when I do this in an in-person setting, what I would do is have you guys introduce yourself to me. I do this for two reasons. One, I like to know something about who I'm working with, and two, I think it gives you guys a chance to learn a little bit about me. So just in case you haven't watched the Sig Figs lecture, I'm Dr. Nanette K. Hartley. I actually prefer Nan, and that's just the way I do things. I am a chemistry major. I went to the University of California, Riverside for my undergrad, and my master's and PhD I got at Arizona State University. I'm here because they pay me, but not just because they pay me, because I care about teaching people something that really most people don't like. And for whatever reason, I love this subject. So that's why I'm here. Now you'll see the next thing we talk about is y equals mx plus b, or apples. I need to know if you're a mathematical person or not. So when you talk to me and you ask me questions, let me know, are you more comfortable with mathematical equations, or are you more comfortable with a concept? Because I can work in both ways. I just need to know which one you prefer. I tend to speak more in mathematical concepts, but if you need me to address things in other ways, that's fine. And then I typically ask my students to define themselves in one word. One word to define who you are. Let me give you an example. My word is stubborn. Why do I say this? Well, because I am stubborn, and that can be problematic. And if I'm going through something and I'm trying to get somewhere and I'm not, it can be a very, very single-minded focus. And so if you want to go in another direction and ask me something, it can be difficult for me to reorient and present that. So understand, it's okay to call me out on that. It's perfectly fine to say, hey, I don't understand. I don't know what's going on. I need you to focus here. And that's okay. I don't mind that at all. It takes a lot of guts for somebody to say, I need you to be where I am. And it also takes a lot of guts to say, I'm confused. I need help. But chances are, if you're confused, other people are confused. So asking the question is, generally speaking, better than not doing so. Okay. So questions, comments, problems on that? If you have questions, comments, problems, I am open to taking any questions that you have. Please try and tell me which lecture we're talking about, the general time in the lecture that we're talking about, what your question is, what I was talking about, and I'll be happy to help you with that. Okay? So when we talk about matter, we can classify matter in terms of a number of different things. So its physical state, i.e. what, is it a gas? Is it a liquid? Is it a solid? That kind of thing. We can talk about its purity. We can talk about its properties. Physical properties that can be observed with no changes to the material. Chemical properties, which require us to do some sort of chemistry to be able to look at what it is. And we can't get back the previous material once we've done that. Things that are intensive, i.e., it doesn't matter how much of it I have. So things that we can talk about for that, density. So mass per volume is something that we can talk about. It doesn't matter how much of it I have. I can measure that. But there are also extensive properties, which is obviously dependent on the amount of the material. If I have a whole nan, the weight of that whole nan is very different than the weight of a half nan. So that's an extensive property. All right. And notice I did say weight because I was talking about me, but when we talk in chemistry, we talk about mass. There is a difference between the two, and I'm kind of neurotic about it. So, not that it matters to you, just that I am. Okay. So, those are the things that we're going to be talking about. So, when we talk about classification, all right, there are 3 states that we recognize as far as this class goes. There are actually 4. So, we have solid, liquid, gas, and then there's plasma. We don't talk much about plasma. It's mostly something that gets talked about in physics classes. When we talk about solid, the molecules are held in a fixed pattern, and it's fixed. I can take this small vial and I can pick it up and move it around, and that doesn't change the way that it looks, how it is. But then there are liquids. Liquids have more space in between the molecules, and they're not in a fixed position, so they can move. What does that mean to me? Well, that means that if I have my soda over here and I happen to turn it in such a way that I allow it to come out of this container, it's going to change the shape that it's in. That's what liquids do. I'm not going to do that because it's messy, but that's what we're talking about. And then there are gases. Gases are more widely spread molecules. They have no fixed position, and they often don't interact with each other. All right. So those are the 3 states that we're going to talk about. Now, it does not require a chemical change to go between these states. So if I have water in the solid form, ice, and I heat it up to take it to the liquid form, okay, that is not a chemical change. That's a physical change, okay? We can talk about what are the changes of state that we have here. We'll talk about this in a lot more detail later, but going from solid to liquid is melting, going from liquid to solid is freezing, going from liquid to gas is vaporizing, going from gas to liquid is condensation, and we can talk about going from solid to gas, which is sublimation. Okay, so those are the things that we talk about in terms of classifications of matter and moving between those phases. We can talk about elements, compounds, or mixtures, and this has to do with the purity of materials. So, what are we talking about with this? Well, an element is something that cannot be further separated by chemical means, right? So, I can't change water except to separate the particles, but I can't break it down anymore and still leave it as a water molecule. And we'll talk about exactly what that means later. Substances are forms of matter that has a constant composition and distinct properties. Okay, so that's a substance. Element cannot be further broken down by chemical means. Compounds cannot be further separated by physical means. Okay, and mixtures are where we have like salt and sand is a great example of a mixture. We can physically separate those things, but and it's not the same process that we'd have to go through if we were going to make a chemical change to it. Okay, so we can talk about the purity of things and what it would take to further separate those from each other. Okay, here are some things. What would I call A? Element, compound, or mixture? I would call A an element. Why would I call it an element? Because there's only one material in this box. Okay, they're all the same color, the same size, so that's an element. Okay, now these in B, they're a little bit different. Not much different, but a little bit different. And that means that I'm going to name them differently. Now, since there are 2 molecules or two atoms that are stuck together here, that makes this a compound. Okay, because it's not made up of single particles. So this is a compound. All right. This could be something like oxygen, where we can't have a single oxygen existing in the gas phase. And so that naturally exists as O2. And we'll talk about that more later. Okay. This is also a compound. All right. Notice that instead of having just one material present, like O2, this is, all of these are the same. They have the same composition. They have the same size. Okay. CH3 is what this could potentially be. But all of them are the same They're just not made from the same element. Okay. But this is also a compound because I can't break it down any further than this without doing some chemical changes to it. This last thing is a mixture because there are ways that I could get these things to separate in physical beings. Okay, so that's a mixture. Okay, questions about that? I hope not, but let's keep going. Pause for just a moment so that I can blow my nose. Thank you for allowing me to pause for there. I apologize for having to do it. So let's keep going. All right. So now we've talked about classification of matter, what we mean by some of those terms. Now let's talk about measurement. So if there's something I want to measure, I need to know a few things. So first of all, what am I measuring? Okay. And how accurate is that measurement? So I have something that's sitting in front of me. Doesn't matter what it is. And I want to measure it. What am I trying to measure about it? Do I want to know how big it is? And if I want to know how big it is, do I care about the actual length of it? Do I care about the volume of it? What is it that I'm trying to measure? The other thing I need to know about is what instrument am I going to be using to do that measurement? Because that's going to determine how accurate that measurement is. Okay, we'll talk about accuracy in just a couple of minutes. And then you're going to see this last part. What are the units of that number? Okay, so now I've decided that I'm going to measure something. I know exactly what it is that I'm going to measure about this thing. I know how I'm going to measure it. What are the units that are going to be used for that? You'll hear me harp on units all the time. And trust me, I'm really neurotic about units. Why? Because there was a situation where there were two teams working together, one being an English team, one being an American team. The English team got some numbers from the American team. The American team just recorded a bunch of numbers and gave it to the English team. The English team made an assumption about what those numbers were and did some calculations with it. And those calculations were inaccurate. Why were they inaccurate? Because there were no units associated with it. And so the conversions that were done were inappropriate. All right. So we need to make sure that we know what those units are. Those units tell us a lot about how big it is, what size we're talking about, what it is that we measured. I can tell from the unit of a number what I measured. So it's important that we report those things. All right. Numbers by themselves are not useful. And we'll talk about this again. But that's what we're talking about there. Now, let's talk about some of the other details about measurement. This is mostly stuff you're going to talk about in the laboratory. The reason that it matters as far as what we're talking about is you need to understand those implications when we do calculations in the class. So what are our base units? And this is actually from a different textbook, but there is a copy of this, a similar table in your textbook. It's table 1.4 and it's on page 15 in your text. So, what are we talking about? Length. The name of the unit is meters, and these are the base SI units that we typically use. Those are symbolized as M. Mass is done in kilograms, or kg. Time is in seconds, S. Electric current is in amperes, A. We don't worry about that too much. Temperature is in Kelvin, K. That we worry about. Amount of substance is in moles and is symbolized MOL. Yeah, because we leave the E off. And luminous intensity, which is candelas, we don't worry about too much. These are called the International System of Units, and they are metric. All right. That means that they're base 10 units. It's a lot easier to work with them than it is with what we call, actually, I typically refer to them as British units, even though they're the ones we use in the U.S. They were invented in Britain, and Britain no longer uses them, but I still call them British units. So, um, when we talk about temperature, we're talking about ways to measure the stored potential energy or the ability to do work during a reaction, that kind of thing. Um, so when we talk about moles, moles are kind of like dozens. So when I say a dozen, I know that that means 12 of something. It's an easier way to talk about, the shorthand of those things. A mole is very similar. It's a way for us to talk about a very large number of particles. We'll talk about how many that is later. Um, all right, I think that's everything. let us move on at this point. So, we talked about base units. Let's go ahead and move on to prefixes. Now, prefixes are what we talk about in terms of how big is a particular unit. So if I'm talking about meters, and you've probably heard this part, if we're talking about meters, but I'm using very small units, we don't necessarily talk about meters themselves. We talk about centimeters or millimeters. Okay, what that means is that we're talking about, hundreds or thousands, parts of meters. So those prefixes indicate how small or how big we're talking about. And what it means is the multiplication factor by which we're dealing with our normal unit. So, like if we're talking about centimeters, we're talking about 0.01 meters. Millimeters is 0.001 meters. So that's what we're talking about with those. We will expect that you can do calculations with that. So if I give you a bunch of numbers and I say, okay, we had this many micrometers and this many this many that, you need to be able to convert between them so that we can do calculations in the class, okay? So that is part of what you will need to be able to do. Scientific measurement. We measure a lot of things in chemistry: length, mass, time, temperature, amount of substance. Please note that mass is correct, weight is not. We take the mass of something, it's not the weight. Why? Mass does not change. Okay, so my mass will not change. It's a measure of how much material I have that is not based on the force of gravity where I am. Weight is something that changes with gravity. So it's different depending on where you are. Now, on the face of the planet, those differences are really, really small. But if we're talking about between here and the moon, those are big differences. So we measure mass, which is constant. Standard units are defined as follows, terms defined on slide 11. Mass is measured in kilograms, metric unit in kilograms. Length is in meters, time is in seconds, temperature is in Kelvin, and amount of substance is a mole. We will talk more about moles. Moles are my friends. So moles are something that we will talk about. So 1 kilogram is 1,000 grams, 100 centimeters is 1 meter, 60 seconds is a minute. Kelvin equals 273.15 plus degrees C. Degrees C equals degrees Fahrenheit minus 32 times 5 ninths. Mole is 6.022 times 10 to the 23rd particles. If it's in purple, you need to know it. All right, now do you need to have it memorized? Ish. You will be able to look and see what information you're going to be given on tests. You will have information to be able to work with those. But those are things that we use so often that it's going to be useful to you to just go ahead and memorize them. Okay? All right. Units matter. Suppose I say I have 12. 12 what? I want that amount to be converted to moles of substance to do a calculation. Well, okay, 12 what? Do I have 12 grams? Do I have 12 particles? Do I have 12 freight cars? I mean, that needs I need to know something more about it. So I can't do that calculation because I have no units. All right. Chemistry in Action, section 1.7 is what I was talking about when we talk about the numbers coming from the US going to Britain and being screwed up because they weren't right. So that's an actual real world example of how this works. It is really important that you understand that this happens all the time. When people don't include units, it happens, and then they have to give those numbers to somebody else to work with. It's a big deal. So we need to make sure that every number that we have, that we write on the paper to deal with in chemistry, or that we write in our lab notebook, has a unit to go with it, okay? Sorry, I needed to do something. So derived units, we can talk about area, which is length squared, volume, which is length cubed, density, mass per unit volume, speed, acceleration, force, pressure, energy. So all of those are based on the base units, but they're combinations of those. These are definitions that you may or may not need. You should be given units that will tell you these things, okay? So if I report something as a volume in meters cubed, you should be able to work with that, okay? Questions, comments, problems about any of that? Hopefully not, but if you have them, please let me know. I apologize. I am sick, so that's why I keep pausing so that I can deal with me being sick. The next thing we're going to talk about is something that it's one of my personal pet peeves, and it's precision versus accuracy. Now, what the heck are we talking about with precision versus accuracy? Well, let's see if I can show you. So let's look at these targets. We have one grouping all together up here in one spot. We have a bunch of them that are all spread out around here, a bunch that are spread out over here, and a bunch that are clumped together right here. Now, you'll see that this first group is listed as precise, but not accurate. So they're precise because they're all very close together. So that means that they're repeatable. Precision has to do with repeatability, all right? But if we're trying to talk about measuring a specific thing, we aren't measuring it, okay? We'd be wanting to get here in the center and we're not. So there's some sort of repeatable error that exists in this, okay, that's leading to this being offset up here the way that it is. So this could be something like an improperly calibrated scale, something like that, that's repeatable, okay? This grouping, on the other hand, while it's not very precise, i.e. it's very spread out, it is accurate because they all lie around that central point that we're trying to measure. This is actually fairly typical for how real-world measurements are done. If everything's set up the way it's supposed to be, okay, and we've taken as much of the error out as we possibly can, this is the spread that we would see from the data that we would take. If we take the mass 8 million times at a particular balance, this is the kind of spread that we would see in that data, okay? We look at this set right here, there is no precision because there's no grouping. There is no accuracy because we're not around that central point. So I have no precision, no repeatability in that measurement, and I have no accuracy. I'm not getting where the actual place I want to be. So the type of measurement that I want. This grouping is both precise and accurate. This is what we want. Okay, this is how we want things to go. We want to be repeatably measuring the same thing, and we want that thing to be what we actually are trying to measure, okay, without any systemic errors to it, okay? So that's the difference between precision and accuracy. You'll notice that most people can't keep those things separate, and actually I have problems with this a lot myself, all right? But that's the difference between those two things. Now, significant figures. Why do sig figs matter? This is why we're talking about this. All right, I want to show you an example of what we're talking about when we talk about sig figs. So, I have two rulers here. I'm trying to measure the same thing. These are both in centimeters. This is 1, 2, and 3, 1, 2, and 3. The difference between these two rulers is that this one has more gradations on it. All right, more gradations means that I'm better able to get the number that I'm looking for, right? So my accuracy should be higher, right? So that's what I'm talking about here. This would give me a more accurate reading. Now, how would I use this in practicality? Well, generally speaking, having used a ruler a few times, I would be able to look at this and say, okay, this is more than 2 centimeters, it's less than 3 centimeters. I know it's more than 2.5 centimeters, so I'm going to say it's 2.7. Okay, why do I do it like that? Well, the way that I do it maybe is slightly different than you do it, but I know that it's somewhere between 2 and 3. This I know. I can guesstimate how far it is between those two Sorta, kinda. Not in a great way, but sorta, kinda. That's important. Now, when I look at this other one, this next one that has a higher accuracy to it, then I can say, okay, we're definitely between 2 and 3. We're definitely above 2.5. I know I'm 2.2, 5, 6, 7-ish, and I'm somewhere between 7 and 8. So I would call that 2.73. Okay. Notice what I did there. I estimated that last decimal again. All right. So that's the expectation in the laboratory, is that you're always estimating for something visual like this. You're always estimating beyond what it actually measures. Okay. Obviously, with a scale, I can't do that unless it's a triple beam balance. But if it's an electronic scale, I can't do that. So some things I can do it for, some things I can't. And so we normally talk about that in terms of, where's my annotation? Sorry, I need my annotate. We talk about in terms of reporting the precision of this. So when I report this as 2.73, I would report this as plus or minus 0.05. And if you ever looked at scientific numbers and the way that they're presented, that's often how it's presented. So you'll see that that's that decimal point that I guessed, and that's how accurate I think I am in being able to guesstimate that number. So that'll tell you how much precision you have with that particular estimate, okay? The same would be true for these two rulers. It's just now, instead of talking about 1, we're talking about 10, okay? So that's what we talk about there. So we need to be able to look at how precise is this, or how accurate is this particular instrument, and then how precise can I be in using that instrument. So how accurate is it? How well does it measure the value that I'm looking at? And how well can I reproduce that to get the same number more than once? Okay. So that has to do with how we report this. Now, I would report that, but it also has to do with how I would interpret that when I see it. If I see that somebody's reported 2.73, I should reasonably be able to know that they have estimated the 3 at the end. And so that may not be as accurate as you would expect the 7 to be. Okay? All right. So that's what we're talking about with those. Let's go ahead on. I want to turn off my annotation. So let me. What numbers are significant? So what the hell do I mean by significant digits? Significant digits are something that I think about in terms of scientific notation. Why do I think about it that way? Because I don't care about the placeholders. What I care about are the numbers that are actually being reported, okay, and why they're being reported. So there are a couple of things that we deal with in terms of this. One of these is very easy to deal with, and that's scientific notation. So if I can get rid of a bunch of numbers by putting it in scientific notation, that implies that those numbers are placeholders. I don't care about those, so they're not significant. The other thing that we can talk about in those terms is, once I've done that scientific notation, what am I looking at? What are the numbers that are left to me? Because those numbers that are left to me give me some indication of how accurate that number is. So if I say there were 10,000 people at a particular event, did I count all of those people? Do I have 10,000 exactly? Or is that a guesstimate? Is it an estimate of something? And the reporting of that number, the way that it's reported, should reflect that, okay? So if we're looking at, and I'm going to skip down for just a second and I'll come back to the stuff at the top. If we're looking at a number like 100, all right, you see this number right here. And it says if there's a decimal at the rear, you hold that 0 dear. Okay, so I bothered to put this decimal point here. That means that I counted there are 100. Okay, if there's no decimal, that's a guesstimate. okay? And what that reflects is that when you go to scientific notation, this number right here would be reported as 1 times 10 to the 2, because it's a guesstimate. This number, on the other hand, would be 1.00 times 10 to the 2. Okay, because I know exactly what that is, right? So that number, again, I'm getting some idea of how accurate that number is based on the reporting that I'm seeing. Okay, so that's how we deal with that portion of it. Now, the other thing that we talk about is what numbers are significant. Well, any number that's not 0 is significant. It's a number. It matters. So a number that's not 0 is automatically significant. If it's a 0, it depends on where it is, whether it's significant. And that's what we've been talking about with the scientific notation. So a 0 that's between two non-zero numbers, that's significant. Absolutely. It's a placeholder, but it's between two significant digits, therefore it's significant. So 101 has 3 sig figs. 1001 has 4 sig figs. If we're talking about 0.01, then we have 1 sig fig. 0.001 is 1 sig fig, and 0.1 is 1 sig fig. So it's only the one that's significant there. Those zeros are placeholders, and therefore would go away if we report in scientific notation. Okay, so that's what we're talking about in terms of those things. So non-zero digits are always significant. 0 digits are sometimes significant. Right, okay. Let's see if we can see that again. Non-zero numbers are always significant. Zeros between non-zero numbers are always significant. All final zeros to the right of the decimal are significant. I bothered to write them out. There's a decimal point. That means that I know them to some level of accuracy. Therefore, I have to keep them. Okay. Placeholder zeros are not significant. To remove them, we rewrite it in scientific notation. And counting numbers and defined constants have an infinite number of significant figures. 6.022 times 10 to the 23rd, the number of particles in 1 mole, even though 6.022 has 4 sig figs, if I'm doing calculations with it, I do not consider the number of sig figs there to be limiting. Okay, so I assume that that is infinitely significant. All right, we'll talk about how that affects our calculations in a slide or two. But that's what we mean by that. All right. Let's talk about rounding. Now, you probably know the rules of rounding. You learned them ages and ages and ages ago, right? Sort of. Yes. For the most part, you probably did. But things get a little funky when we start talking about actual scientific rounding. Okay. So if we're talking about rounding, if the digit immediately to the right of the last significant figure you want to retain is greater than 5, you round up. Less than 5, you don't change it. Okay. Awesome. I get that. But oh crap, what if it's 5? What happens then? If it's 5 followed by non-zero digits, then I increase the last digit by 1. Okay, so it's 0.76581256. Then it goes up. All right. What if it's 5 and it has nothing after it? Then what do I do? That's the weird stuff. All right. In order to be statistically significant, we have to find a way to deal with these in a systematic way. We can't always round up. We can't always round down. And as people, for whatever reason, we will have a preference for rounding up or rounding down. Personally, I like to round down. It's just what I do. But that's not a reasonable thing for me to do, because if I round down with everything that I do, or leave it flat and don't round it up, then that's not an accurate representation, or there's no precision in the representation. And as I continue to do that, what what we call that error propagates. So it gets bigger and bigger and bigger as I do more and more and more calculations. All right. We want to try and avoid that. So the way that we avoid that is by looking at these two rules at the bottom. And so if it's 5, not followed by a non-zero digit, then there are two cases that we have to consider. If it's the number before that, so if we're talking about 2.835, the number before the 5 is 3, so it's odd, then I'm going to increase that last number to 2.84, okay? If, on the other hand, we're talking about a number like 2.65 and the number before it is even, then we're going to leave it alone, okay? So now we're talking about the number before the last digit. If it's odd, we round it up. If it's even, we leave it alone. Okay, so that's how we deal with that. That way, systematically, we're going up sometimes and down sometimes, right? That's why we do that. Now, scientific notation. We've been talking about it. I've been talking about it. Oh my God, what if I don't know what scientific notation is or how to get there? Well, it's important that we then talk about that. So, what are we talking about? Scientific notation involves moving decimals. So 1.5 times 10 to the 4th. Because the exponent is positive, it moves the decimal point 4 places to the right. Positive moves it to the right, and 4 moves it 4 places. So 1.5 then goes 1.5, 1, 2, 3, 4. And this is my result. Okay. If we're talking about 5.8 times 10 to minus 4, the negative 4 moves it to the left 4 digits. So 5.8 is where I start. Then I go 1, 2, 3, 4, and I end up with this number right here. Okay, so that's how we can put it back. That's how we get from scientific notation back to a real number. Now, if I'm on my calculator and I want to talk about what is scientific notation versus what is not scientific notation, then there are ways for us to talk about that. I'm going to show you my calculator. This is the one that I use. If I have 1.5 second EE4, that's this number right here. I hit enter, and shocking, that gives me the same thing. And that's because it took it out of scientific notation and converted it to a regular number. Well, what if I don't want that? What if I want it to stay in scientific notation? Can I do that? Actually, yes, I can. And the way that I do that is to click mode and go up here to sci and hit enter. Then I go second quit, and then I multiply that by 1, and I get back to the scientific notation that I had. So if you want to put it in scientific notation, you can. If you want to turn that off, you can. That's typically how you do that. Not all calculators are going to be exactly the same, but you should be able to Google for your calculator how to do it. And if you can show me your calculator, I can probably show you where it is, because that's kind of what happens when you're a teacher of science. You need to figure these things out. So that's how we do that. Now, understand 1.5 times 10 to the 4th gives me that same number, okay? In that case, it doesn't always, all right? So make sure that when you're putting it in scientific notation, you're using this EE key and not the times 10 to the 4th like this, because if you do that, you eventually end up with systematic errors, all right? So we need to make sure that we're avoiding that, okay? So let's go back to our slides. Oh, scientific notation. We're gonna practice. Oh, practice. Awesome. How do I practice? Well, if you're anything like me, I don't practice without writing crap down. So, how am I gonna write crap down? Oh, all right. Oh, hold on. Close that for a sec. I have a fancy toy. Give me a second. So I can't do anything without writing stuff down. So could have sworn I just fixed this. Sorry. Okay, fancy toy. I can't do anything without writing stuff down. So I'm going to write down the stuff that was there. 2.13 times 10 to the third. It's the first one I asked me to consider. 7.5 times 10 to the negative fourth. 9.8 times 10 to the sixth. And 5.67 times 10 to the minus eighth. Okay, awesome. So how do I practice this? 2.13 times 10 to the third. So it's positive, so I'm moving to the right. We're going to go 1, 2, one more. So that's 2, 1, 3, 0. Okay. Negative, we're going to go 1, 2, 3, 4. So 0.0075. Because I moved to there, and then I have 3 decimal places I need to put in front of it. 9.8 times 10 is 6. We're going positive. So I know it's going to be 9 and 8. That's 1. So I need 5. 1, 2, 3, 4, 5. If I do commas, that's then like that. And then 5.67 times 10 to the minus 8th. I know that I'm going to move this 1 here. Then I'm going to need 7 decimal points. 7 zeros. 1, 2, 3, 4, 5, 6, 7, 5, 6, 7. And I'm looking at this right here. 1, 2, 3, 4, 5, 6, 7, 5, 6, 7. So that's how I got to all of those things. That's the practice that I wanted you guys to do. Now, what happens when we do calculations with sig figs? Oh, Lord. All right. So we've done sig figs. We talked about significant digits. We talked about when 0 matters. We talked about rounding. Now we have to talk about calculations. So when we do calculations, there are 2 basic cases that we need to worry about. One is addition and subtraction, and one is multiplication and division. We will spend far more time dealing with multiplication and division in chemistry, but we need to be able to talk to both. When we do addition and subtraction, we're looking at how far past the decimal point we are. That determines how much accuracy we have for those numbers. Since I may be measuring many, many different things, I can't get any more accurate than the least accurate number that I measured. So if I have 12.6 and 6.2, then those are both, 1 decimal place, right? But I have 12.6589 plus 12 plus 6.8. I can't be any more accurate than 6.8. I can't develop accuracy in that calculation, all right? So we have to limit by that number that has the least places past the decimal point. That's what we're talking about. So for addition and subtraction, it's the number of decimal points past the decimal place, to least precise decimal place, okay? When we talk about multiplication and division, that's completely different. There, we need to know the least number of sig figs. So when we do multiplication and division, we're limited by how many sig figs are in our least accurate number, okay? So we're talking about 12.74. Okay, fine. 12.74 is 4 sig figs, so my answer needs to have 4 sig figs, okay? So that's what we're talking about for that. Questions, comments, problems on any of that? Like I said, as we move forward, we'll see where that applies. We'll see the addition, subtraction in, specifically when we talk about molecular masses, things like that. And any other conversion that we do is probably going to be multiplication and division. All right? Questions about any of that? Hope not. let's start talking about my favorite topic in the universe, dimensional analysis. What the hell is dimensional analysis? Dimensional analysis is a method of doing math that involves units. Now, why? Why would I do this? I'll give you a real specific answer. I didn't really understand physics. I don't like it. I didn't really understand it. It didn't make a lot of sense to me, but I knew what units each of those numbers were supposed to have. So if I was asked to calculate something, I knew what units it was supposed to be in. I could look at the numbers that I had and figure out how to get from where I was to what I needed and get it. Chances were, if I got the right units, I got the right answer. That's what this is based on. Okay, we also call this the factor label method for converting units. All right. And you'll see there are a couple of examples here and a whole bunch of text. Don't worry about the text. We're going from miles per hour to meters per second, right? I have 10 miles per hour. I want to convert that to meters per second. I need to know how many miles and how many seconds, or how many meters and how many seconds. So I need meters per mile. That's a conversion factor. And I need how many seconds in an hour. That's a conversion factor. So if I take my 10 miles per hour, this side is miles per hour, I multiply by the number of meters per mile, that cancels out the miles. And that leaves me with an answer in meters. I then want to convert from hours to seconds. So I take and I multiply by the number of hours in how many seconds are in an hour. That gives me an answer in meters per second. I cancel out the hour here. I cancel out the mile there. So there we go. Woohoo! Yay! Now, unless my calculator burps, which happens, or I do something messed up, or I write down the wrong conversion, or whatever, we're going to be okay. All right? It's very easy to do this. There are only a couple things that we need to worry about when we do it. One is, how do we set it up? And I'll show you that in a few minutes. And two, make sure that every unit, every single number you have comes with units. This gets way more complicated as we move forward. When we get into gases, you'll be really happy that we did this. In the beginning, it's not so complicated. Let's talk about one more example. Oh, dear God. So what am I looking at here? Well, this first row is all conversion factors. I have number of feet in a mile, both as miles per feet and feet per mile, minutes per hour and hours per minute, minutes per second and seconds per minute. If I want to go from miles per hour to feet per second, then I have to go from miles per hour and convert. I always start with the stuff that's on the top. So 50 miles, and I want to go to feet, then I take this feet per mile and put that in here. So 50 miles per hour times 5280 feet per mile. Okay, that cancels my miles. At least you have an answer in feet per hour. Closer, but not there. Now I need to get rid of the hours, and I want to go to seconds. So I know that 1 hour is 60 minutes. So 1 hour, 60 minutes. I cancel my hours. That leaves me with feet per minute. Close but no cigar. 1 minute is 60 seconds. So I multiply that in. That leaves me with feet per second, which is what I want, which is this. Okay, that's what we're talking about with that. All right. So that's what we're going to be doing. And that's what you'll see me doing when we do this. Now, the other reason that I show you this is that you can see this thing right here. What the heck is this? And I talked about it. I alluded to it, but I haven't talked about it specifically. 50 miles per hour is where I started. So that means that I had miles per hour. So this is division through this line. I multiply that by feet per mile. So multiplication across the vertical lines, division across the horizontal lines. Okay, that's what we're talking about. I call this the railroad method of setting this up. I know that this was taught to me, and I didn't necessarily like it when I started. I was a big fan of parentheses as opposed to this. But then the parentheses got confusing, and I got into places where I was having to do 20 different calculations, and didn't didn't want to disconnect them all, and you know, so I stopped doing it that way and I started doing it this way, and now I understand why it's done the way it's done. I don't frankly care how you do it on your test. If you want to do it this way, that's great. If you don't want to do it this way, that's fine. Here's the thing though. I will not, under any circumstance, give you credit for a number that you have come up with if I cannot see some layout of the logic of how you got there. Okay? So if I tell you to go from 50 miles per hour to feet per second, and you say that it's this number because you calculated it on your calculator and you think you don't have to show me anything, the answer is no. I don't care that you got the number. That's not what I care about. What I care about is how you got there. And so I need to see how you got there. All right? You need to show me that. So that's what I'm concerned about. This is why I ask for and will expect that you turn in your scratch work. Okay, and I mean it when I say that I will not give you credit for the right number without having any work to show for it. I won't. Okay. So here are all of our happy units. All right. Why do we need all of these happy units? Well, we need all these happy units so that we can do some examples. Now, I'm going to pause for just a few minutes so that I can do something. Bear with me just a moment. Apologize for that. I had to move a few things around. So we need all of these units to be able to do some of these examples that I have over here. So these are dimensional analysis examples that I've put together. I have presented these to you without answers so that you can try them on your own. And then a couple days later, you will get the answers for each of these things. Okay. So that's how I do that. I want you to take the time to try and work on these on your own. Now, if I were in a physical class, what I would do at the end of each lecture is to walk through how each of these work. Now, since I'm giving you the answer keys, I'm not going to do that for you guys. But I am going to do one example here, show you exactly how I would do this. And then you guys can work through that as you see fit. So, the first thing that we're looking at here, it says the label on a soft drink bottle gives a volume in 2 units, 2.0 liters. I'll show you what I'm doing in just a second. And 67.6 fluid ounces. Use this information to create a conversion factor between the English and metric units. Right. So what does that mean? Well, that means that I want to know how many liters or how many fluid ounces. That's what I'm looking for. And so I can simply set this up as 2.0. Let me get it back. Give me a second. So it says that they're 2.0 liters, 67.6 fluid ounces, if I correctly. Let me check that. Yes. So if I want to set up a conversion factor for that, there are two ways that I can do this. One, I can say that 2.0 liters is 67.6 fluid ounces. Leave it like that. I could leave it as 67.6 fluid ounces is 2.0 liters. Or I could do the conversion or the actual mathematics on it and say that 1.0 liter is whatever that number is, because I can't do that math in my head. So, hey, that's what I have a calculator for. 67.6 divided by 2. 33.38. So 38.8. 33.8. Or 33.8 fluid ounces in 1.0 liter. Okay, that's what we're talking about in terms of making our own conversion factor. Now, is that the only thing I need to do? No. Is it the most interesting thing I need to do? Maybe. Maybe. Let's talk about a couple of other things. And let's go one of the big ugly ones at the end. In a recent Grand Prix, this is the last one, the winner completed the race with an average speed of 229.8 kilometers per hour. 229.8 kilometers per hour. Keep getting my decimal places to the wrong place. 229.8 kilometers per hour. Actually, that's H. And I want to know what that is in miles per hour, meters per second, and feet per second. Okay, awesome. Now that I've written a few things down, let me look at some of the conversion factors that I was given. What do I see? Well, I see that 1 mile 1.60934 kilometers. Okay. So I can go from kilometers to miles. That's awesome. Now, I can go from kilometers per hour to meters per second with a few of the other conversions, because I know that there are 1,000 meters per kilometer, and I know that there are 60 seconds in a minute, and I know there are 60 minutes in an hour. I need to know how many feet are in a mile or something like that. So let's see if I have one of those. 1 foot. 1 foot is 0.3048 meters. And I know that this is probably gobbledygook at this point, but I know that's what I need. How the heck am I going to do this? Well, that's where the fun comes in, and that's why I'm showing this to you, so I can walk you through my logic for getting from where I am to what I need and how I set that up. So I know that 229.8 kilometers per hour, right? And I want to go to miles per hour. That's the first one they asked me for, so that's the one I'm going to do. I know that I have this unit right here, so I know that 1.60934 kilometers in 1 mile. And so if I do that math, that kilometers cancels and I get miles per hour. Okay, awesome. That's exactly what I'm looking for there. So how do I do that? Well, 229.8 divided by 1.60934. Those are the numbers that I was given. I get this big, huge number here, 1.94279, blah, 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 blah. And then I start thinking, okay, how am I supposed to know how many sig figs I have? Here's where we talk about sig figs. This conversion factor that I was given is considered infinitely known. So this one is never going to limit what I talk about. So the answer that I need to think about is how many digits were given to me here. 4 sig figs in that number. So my answer should have 4 sig figs. 4 sig figs from what I have there, 1.427. Does it stay 7? No, because the number after it is 9, so it's 1.428. 1.428 times 10 to the 2. And my units are miles per hour, which doesn't fit, but there you go. Okay, awesome sauce. Now, I need more space, which kind of sucks, but I can cheat. I can. copy this, paste it here. No, yeah, thank you. Make sure I put that back there. Yay. Okay, awesome. So now I've done this one. That answer I have. It's on that previous page, but I've got it. So now let's talk about 229.8 kilometers per hour. And I want to go to meters per second. All right. So how do I get to meters? Well, there's 1 kilometer is 1,000 meters. Okay. So that gets rid of my kilometers. Then I have meters per hour. I don't want meters per hour. I know that 1 hour is 60 minutes. Get my hour. And then 1 minute is 60 seconds. Get rid of my minutes, at least we go seconds. So if I do all that happy math, 29.8 times 1,000 divided 60, 6.383 times 10 to the 1. Okay, fine. I know I still have 4 sig figs from the 229.8. So 6.383. Next number is 3, so I leave it 6.383 times 10 to the first. And that is meters per second. Woohoo! All right, now I'm done with that one. Now we need to go to feet per second. So I can set this up the same way that I've got here. And that leaves me with an answer in meters per second. 229.8 kilometers per hour. 1,000 meters per kilometer. 1 hour. 60 minutes. 1 minute. 60 seconds. Minute. Hour. Kilometer. Now I need to go from meters to feet. Okay. 1 foot. 3. Sorry. Wrong place. 0.3048 kilometers. Oh, so meters. 8 meters. Meters. That's getting me feet per second. Yay, that's what I'm looking for. Let me do all that happy math. Now, this number that I calculated here was all this stuff through this, right? So everything up to there. So now I just need to divide that number on my calculator by 3048. Hit enter. I still have 4 sig figs for the number that they gave me. Because again, the conversion factor that I'm given here is considered infinitely known. So I'm not worried about that. So 4 sig figs is what I'm looking for. 2.094. 2.094 times 10 to the 2 feet per second. Okay. And that's the way that I handle all of this, is I leave those calculations the way that they are, and that way I can deal with them later. Now, since I was asked to report something that was part of the calculation that I did for the last part, I will report that in the correct number of sig figs right here, but I didn't change it when I do this calculation here. It's not like I took this answer and then did the division from here. I did it with all of the decimals that were here to make that work. Okay, so that's what I'm talking about in terms of how do I report my sig figs? How do I think about my sig figs? What do I do with my calculator? All of that stuff. So that's how all of that comes in. Now, I hope that didn't leave you with any questions, and I hope that gives you some idea of how I set things up. If you are interested in seeing more of how I set things up, then let me know. And I can put together another set of conversions for you guys so that you can start looking at that. Okay? All right. I think that's everything for now. I appreciate you guys being with me, and I apologize for being sick and all the rest of it. I will talk to you guys soon. Thanks. Hope you have a great day.